Good morning, everyone. Okay, so welcome. Nice to see most of you back here. Okay, so as I always mention, even though I upload the recordings and you can view them, it's always good to just drop in for the lecture. Okay, okay, so that at least you listen to it live and you have some things that you absorb. All right, which makes it easier for you when you maybe look at the video or the recording later on. All right, so it won't be like new material. Okay, so it's always good to just come in for the lectures even though it's recorded. Okay, so let me get started. All right, so along the way, I just uploaded a new updated version of the project specs. All right, I'll talk about that. And I also talk a bit about this week's lab. Okay, what is going to happen. Okay, so all of that will be coming along the way. Okay, so let's get started. All right, so we have quite a few things to cover today. So everybody can see my screen here. Okay, thank you. Okay, so just again, in case I get dropped off, all right, a disconnect or anything, just stay on. All right. Usually what happens is Zoom will randomly assign somebody else to be the host. Okay, and then once I come back in, I will take over. Okay, so if I get disconnected, just stay on the line. Okay, and if suddenly for some reason you can't see me, you can't hear me, you know, or something like that, then just one of you can just call my handphone directly. All right, at least I know that something is wrong on my side. Okay, so let's go on with this chapter. So last week we covered the basic introduction. We talked about some project specs, all right, and some motivation behind what we want this module for. All right, so let's go on to some software design basics to just recap where we are, all right, and how we can achieve what we want to achieve. Okay, so in terms of concurrency, so this chapter I would say is fairly more of a recap of things you already know, so I'll go a bit faster. All right, just to make sure that we understand the motivation behind what we want to do. All right, so we talked about this last week. All right, where we said that microcontroller itself, all right, already has its own processor core. So in this case, ours is the ARM Cortex M0 plus core. All right, followed by a whole bunch of peripheral subsystems, right, like analogs, timers, communication, DMA, and so on. So all of this helps us to have a very a complete system that is able to work together well, all right, without actually anything much. Okay, so so we saw that we already have most microcontrollers have sufficient subsystems to actually support concurrency with the hardware, as well as what we already know about interrupts. All right, so we already are able to have a high level of concurrency. All right, so this is an example we saw last lesson. All right, so I will not go through this again, but basically by configuring some hardware interrupts, okay, to happen at some periodic interval, all right, certain things can always happen in a real-time manner while you have a main loop, okay, that is running at the back end. All right, so this sort of already allows us to have some level of concurrency. All right, so that is good. All right, because when you finish this course, all right, you will see that how sort of powerful and fantastic having RTOS is, all right, because it can really allow you to think concurrently and design very complex systems. All right, but having said that, okay, I always tell students the same thing. You do not necessarily do an overkill and put an RTOS in a system that doesn't actually need it. All right, so even though you know and you already learned RTOS and you know it's very, very useful, but in many applications, maybe you don't even need a RTOS. All right, the microcontroller with its hardware and interrupts may already be sufficient to solve whatever is the requirements of the system. Okay, so we don't always overkill. All right, if we can do without the RTOS, we just go ahead and do without the RTOS. Okay, but if we really need it, okay, it really helps us, then we go ahead and integrate it inside. Okay, so in terms of the scheduling of the CPU, of course, we don't necessarily have any particular scheduling because we just go ahead to write everything in the main loop, plus we have interrupts. All right, so of course, what we want is we want to make the processor more responsive. All right, so the responsiveness comes naturally when we have the hardware-driven interrupts. Okay, because the moment the interrupts come in, the processor is able to respond. All right, but how do we manage if I have a lot of software threads? That means a lot of software routines that are written, all right, that also need to have some form of responsive nature from the processor. Okay, so if we look at this example, all right, we know that the interrupt, okay, whenever interrupt comes in, all right, there are a few things that happen. So firstly, we know that there is this concept of saving the context. All right, so if you remember from EPP2, okay, you have learned this before, where when the interrupt is coming, you are actually busy doing something else. All right, you are in the midst of executing some other instructions. So to service the interrupt, you need to finish what you're doing first. Correct. So that takes some time. And when you finish what you're doing, and then you need to save that context, okay, the register values, the program counter, and things like that. And after all of that is done, all right, okay, then you are able to go ahead to finally switch over to the interrupt. So that is what is happening here. So at this point of time, all the processing of the earlier stuff, the saving of the context is done, and you can now switch over to the interrupt. All right, once the interrupt is done, then you what you call restore the context. Okay, restore the context, and then you can continue from where you left off. All right, so this is basically the idea of interrupts, all right, which we or how it works. Now, this is of course handled in the back end. All right, we don't really bother about it so much because once we configure the interrupt, we configure all the flags and all this stuff, it happens automatically. All right, so we don't really worry about that so much. Now, how do I manage the software? Okay, to sort of share the CPU stack. So when I'm not servicing the interrupt, I'm running my main software, but the software itself may have different activities that I want to carry out. So how can I do it? All right, so this is the example we saw again last lesson. So this is a fairly simple system, all right, where we say that just interrupts and the main loop is enough. All right, so you don't really need to do much. Okay, you have a basic system where you do the necessary initialization. All right, and then subsequently you can just put it into a sleep mode. All right, and you let the interrupts handle all the activities. All right, so things like keeping track of the time, handling the user interface and the sensor rotation. I mean the sensor whenever the wheel rotates. So all of this can be handled through interrupts at the back end. So this is of course a fairly simple system. So you can sort of just manage it this way. How about something like this, which is a more complex application? So this is not really something that you see in Singapore much, all right, potholes. Okay, so in Singapore, I think we do quite a good job in maintaining the roads, all right. So even if you see potholes, usually they get cleared and covered up very quickly, all right, so it's not really an issue, all right. But of course, in some countries, maybe it is a common issue, all right, because it takes time to really manage all of this. Okay, so a system that is able to detect and warn you ahead of time that there are potholes is something that is beneficial, correct, to maybe people living in that area. Now, if I look at this system, all right, what are the things you need? All right, so you need things like you need a GPS, you need switches, you need a speaker, okay, you need some user interface, you need memory, and so on. Okay, so how do I manage all of this? So this is of course a more complex system, okay, compared to what we saw with the bike rotation sensor. Okay, so let's look at this in a bit more detail and try to understand how we can go about doing this. All right, so if I look and break it down into a series of software tasks, okay, so I can say I firstly need to decode. So whenever the new GPS data arrives, okay, I will need to decode this new GPS data to find what is the current position. All right, then I need to do a check, okay, because I will have a database, correct, that tells me where are all the locations, and then I need to do some form of checking to know whether I'm actually nearby any of the potholes. All right, and of course, you may also want to do a recording or updating of the database. Okay, so maybe you have notice a pothole which is not in the database, so you can also update the database. So you can do a recording to record this position to the memory. All right, and of course, while all this is happening, you also need to be able to respond when the user presses any user interface buttons. And at the same time, you may also have some LCD or some display to tell the user what is happening. Okay, so again, this is just an idea only, correct? If you were to design this, of course, you may have more tasks, you may have lesser tasks, and so on. But this sort of gives us some rough idea of the various activities you need to carry out if you were to design such a system. Now, the important thing is, if let's say now I stick with a normal microcontroller, correct, and I need to run all of this. Okay, how will I go about scheduling them? Or how do I go about scheduling them such that I'm able to fulfill the requirements of the system? All right, so I have 5 different tasks. Okay, and how do I go about doing this? So let's go ahead and look at it in different from a different perspective each time. Okay, let's take the easy way out first. Okay, so the easy way out is I just write each of it as a function. And I just run it as a while loop, okay, function by function. Okay, this is of course the very easy and straightforward way to do it. Okay, and will it work? Yes, it will work, but how well it works is another question, correct? Okay, how responsive is it going to be? Okay, in terms of giving you up-to-date real-time notification. All right, so it can work, but how effective it is another issue. All right, so the issue comes is, what if the GPS data arrives right after I pass the decode function? All right, because we know that if I look at this sequence, the decode is the one that is supposed to process the GPS data. Okay, but what if the GPS data, because GPS data is coming in a non-periodic manner, correct? We do not know when the next updated value will come in. So as and when the GPS module receives it, you will be able to update that there is a new information. All right, but since I'm running it in a sequential manner, all my sort of routines, okay, if my GPS data arrives just after the decode function has finished, then what happens? I need to wait for one complete cycle. Okay, until here. Okay, before I can decode this new data and perform the check. All right, so you can see that it is going to be quite slow. All right, by the time from the time the new GPS data has arrived, okay, to the time that I actually am able to decode it and perform the checking to say that the pothole is nearby or not nearby. All right, so by the time you may have already driven over the pothole. Okay, so this is of course not a ideal solution, all right, because of this non-deterministic response of the system. All right, again, this ties in because of the fact that we ourselves don't know when the GPS data is going to come in. Okay, so you can see that if I were to do this kind of what you call static scheduling, all right, it is going to be a bit more of a challenge. All right, now the next is what we call, I can do dynamic scheduling. Okay, so in dynamic scheduling, I schedule tasks based on importance. All right, so based on the importance of the events that are happening, I can decide who is going to run next. All right, and this also has 2 variations to it. One is what we call run to completion, or the other is preemptive. Okay, when I say run to completion means a task, once it started, will run until it finishes, and then the next task will take over. If I were to say that it is going to be preemptive. Okay, that means when a task is running, I can actually stop it halfway and allow somebody else to take over. All right. So in this case, all right, if I were to perform the dynamic but run to completion, okay, run to completion, what would happen is if my GPS data arrives here, that means this was actually decoded. Okay, but just after decode, all right, the GPS data comes in, and I know that the GPS data has arrived. I can dynamically change the order. So instead of the usual order, after record, I'm able to initiate the decode to run again, because the decode is now considered more important since a new GPS coordinates have been received. All right, and then I do the check and so on. Okay, so this is of course a lot better. Okay, if I'm able to dynamically change my sequence or schedule. All right, so this is of course one good way of responding. Okay, and of course, how you can do it is you need to keep track of the state of the various tasks. Okay, so we're going to go into more detail on this, okay, when we start the OS. Okay, so I don't want to go too much about it right now, but basically the idea is that when you create tasks, okay, so what do you mean by task? So we can relate tasks, okay, in a simple way to say that it is some specific function. Okay, so you can think of it as a function now. So the decode or the record, okay, or the store, everything is considered a function, and we can do a easy relation now to say that function is a task. So I want to run a particular task, but the task that I'm going to run next always depends on who is the highest priority task that is waiting. Okay, so what will happen is if I go back here, the original sequence is after I do the record, I'm supposed to check for the switch. All right, so the original sequence was after record was supposed to be switch. Okay, but okay, because the GPS data arrived, I am able to dynamically switch. Okay, so what happened was this was record and this was switch. Okay, but because a new data arrived, the GPS data came in. All right, so the decode, all right, that was originally in the waiting state, okay, got promoted and went to the ready state. Okay, so the switch went to the back of the queue and decode took over. Okay, so the switch is no longer the next in line. The highest priority task is now decode. So that is why the moment a record finishes, the decode task will be able to take over the CPU. Okay, running, when we say a task is running, that task is the only one that is using the CPU. The rest of the tasks are either in what we call the waiting state or ready state. Okay, the ready state is the next task that is going to take over the CPU, while waiting means you are still in the queue, not yet even ready. All right, so this is just a simple way of scheduling, all right, different functions so that whatever is most important will get to take over the CPU next. All right, now the better one is of course what we call dynamic and preemptive. So preemptive basically means that in the same scenario, okay, I finish the decode, okay, I start the record, but the moment I start the record, the GPS data came in. And since the GPS data comes in, I will be able to immediately switch out from record and go to decode, because the decode is now considered more a higher priority. Okay, so this allows me the most efficient response time, right? Because I'm able to preemptively switch out from a task to go to another higher priority task. Okay, so that is the dynamic preemptive scheduling. Okay, so if you compare all of this, okay, definitely the dynamic preemptive is of course the best option. Okay, but of course this is not so easy. But theoretically, when you talk about it, yeah, we can say that okay, this is how it's supposed to be and this is how it's supposed to run. Okay, but it requires a lot more complicated programming, a lot more memory, and it also deals with other, or also introduces other challenges. Okay, things like data race conditions. Okay, which we will talk about more when we deal with the OS. Okay, so even though theoretically it sounds very good, okay, implementing it is a lot more challenging. All right, and it also brings about other challenges, okay, and other issues which we need to deal with. Okay, so again, these are the schedulers that we just reviewed. Okay, so there's a question for the dynamic preemptive. Does a task that was interrupted halfway gets done after the high priority task gets executed finish? Okay, so again, it depends on how the scheduler is written, right? Because if you go back to the sequence here, okay, if I'm preempted in record, okay, if record was running and then I'm preempted, then because a new data came in, then I switch to decode. But after decode, the sequence is that check must be run. All right, so again, there is some other dependency here that if I do decode, I must do a check. Okay, so the scheduler must also know how to look at what is the expected sequence so that you do not jumble up the sequence. All right, so even though you are in the midst of something, you get preempted, but once you get preempted, you have to still follow the correct sequence so that the data doesn't get sort of misinterpreted along the way. Okay, so again, this comes down to, again, very at the back end, more complex things that needs to be handled. Okay, so the previous task, technically you can say that it gets dropped, all right, until the next time that it's scheduled to run. Okay, so of course, when it gets scheduled to run the next time, it must also know that it is going to deal with a new set of inputs, not the old set of inputs. All right, so that is where this issues of making sure it has the correct data is important. Okay, because when the record first started running, okay, when the record first started running, it had the old GPS data. All right, but the next time that I run record over here, I must make sure I use the new GPS data. Correct. So there must be some way in which the correct data gets updated so that follow-on tasks or functions use the correct data when they are scheduled to run. All right. So again, these are all challenges that we need to deal with. Okay. Okay. So does the previous task get redone from the beginning? Again, it depends on the nature of the task. Okay. And what we are trying to do. Okay. So in some cases, it may have to restart from the beginning. In some cases, it will get dropped. It will carry on from where it left off. Okay. But again, for it to carry on from where it left off, we need to see whether the data is still valid. Okay. So that is where other checks need to be in place. So it's not just the scheduler that decides whether it's carrying on or start from beginning. It is also the actual code that is being written in those functions. So the record function must also be written correctly to know that if there is new data available, then I need to restart. If it is still old data, then I can continue and so on. Okay, so there are more things that need to be done at each task level, okay, in the code to make sure that the correct information is being processed. Okay, so in terms of the schedulers, okay, so these are the ones that we just saw. All right. Again, I just showing some examples of how it can be sort of doing some pseudocode, how it can be done. So if you talk about a very simple cyclic executive with interrupts, okay, that means you run everything in sequence and then you use interrupts to handle it. Okay, so one way is you can say that you have a while loop, okay, and the while loop will always check for the interrupts being triggered. So if any interrupt is being triggered, then I say that request is true. Okay, and then I finish. Okay, once that check is true in the main loop. Okay, so if you again recall, one of the things we discussed in EPB2 is your interrupt handlers should always be as short and focused. Okay, so when we say short and focused, basically mean that we want to know what is really urgent, what is really important in the interrupt. Okay, and that is usually capturing the new data and storing it somewhere. Okay, the back-end processing of it is usually sort of delegated to another task, or in this case is completed in the main loop. Okay, so that is why we say that we do the urgent work here and then we finish off the work here in the main loop. All right, so that is basically one way in which you can handle or develop your code. Okay, Cyclic Executive with interrupts. Okay, so this is not a RTC interrupt. Okay, so this is I mean, in a sense, you can say that. I mean, yeah, in a sense, you can say this is a. I mean, not run. When you say run to completion, it will not necessarily complete because if I'm in the midst of finish device A, okay, I might still get interrupted again. All right, so it's not to guarantee to say that I will complete the device A work without interrupt. Okay, again, you can always change the behavior if you want, all right, because in the software you always have the flexibility to disable interrupts and enable interrupts again. Okay, so for example, if I really want to make sure this is RTC, I can say that in the beginning I disable, okay, interrupt, okay, and after I finish I enable interrupt. Okay, so this in a way can help to ensure it runs to completion. Okay, but again, these are just tweaks you can make, okay, depending on what is the behavior you want. Okay, run to completion scheduler basically, okay, basically what it does is, like I said, it allows you to run, okay, until you finish. All right, so in order for you to do it, all right, you can implement it many different ways. Okay, so here they just give you an idea of how it can be done. All right, so one way of doing it is you can use a table. All right, so you can have like a table, okay, in your software to keep track of how much time, okay, any particular task needs. All right, and once that task is complete, all right, then you are able to switch over to the next task and so on. All right, so you always examine the scheduling table, all right, before you decide what to run next. All right, and how often you manage this table, you can use a periodic timer. Okay, so this is just one idea of how I can implement a scheduler that is able to dynamically switch between the various tasks. All right, so this table, all right, so this table will have many entries. Okay, so task 1, task 2, and so on. But again, it can always change. All right, so it can always change. That means when something happens, I can always rearrange the sequence in the table so that maybe task 2 is now more important. So task 2 will run first and task 1 will run later and so on. Okay, so when the next timer interrupt happens, whoever is in the top of the table will be scheduled to run. Okay, but in the meantime, this table can be rearranged, okay, before the next interrupt happens. Okay, so you can see that implementing this kind of scheduler on your own is quite complex. All right, and it's not an easy task. All right, so that is where actually the OS comes in. Okay, so when we are going to when we switch over to the OS part later, you will see that all of this is actually very nicely handled for us by the OS. So we don't need to worry about this so much. Okay, the only thing that we need to think about is what are all the tasks we want in our system and what or how they will communicate with each other, how they will synchronize the data and things like that. All right, this lower level implementation of the scheduling and the policy behind it is actually managed by the OS very nicely. Okay, so that is the good part of integrating an OS. Okay, preemptive scheduler again is even more complex, all right, because you are not going to run to completion, all right, and that means that even though the response is very good, all right, you need to be able to handle all the potential problems it brings along with it. Okay, so that is why the OS, okay, the OS is really a blessing, because it actually helps to, it gives us the tools. It doesn't solve the problems, okay, but it gives us the tools to handle all these problems in a very, very nice and elegant way. All right, so when we introduce the OS, we also need to make sure that we handle these problems in a nice way using the tools that the OS gives us. All right, so that is what we will be studying when we switch to the OS part. Okay, so in terms of the scheduling, okay, so in the earlier scheduling diagram, this arrow wasn't there, if you notice. Okay, and why this arrow is here now? Because we are now talking about it being preemptive. That means a task that is currently running, okay, can suddenly switch and go back to the ready state. Okay, why? Because somebody else is higher priority. Okay, so the example is what we saw just now, where the record is running, okay, but it hasn't finished. But even though it hasn't finished, the new GPS data has made the decode task higher priority. So the decode task is now supposed to run. Okay, and since the decode task is going to run, the record task will has to be switched back. Okay, so the decode is going to come here, and the record that was originally here has to go back to the ready state. Okay, so this is basically sort of give you a glimpse of actually how the OS is going to work. Okay, it's going to continuously help us to identify the highest priority tasks and do this switching for us automatically in the background. Okay, so all of this dynamics is handled by the OS. So we focus on the idea of the high level objectives that we want the application to achieve. Okay, so that is basically what the OS or the RTOS is all about. Okay, so what we want is to have the maximum response time. I mean, that means the fastest response time, okay, given the requirements of the system. All right, so this involves many different things. So the first thing is, of course, the scheduler. Okay, so the scheduling policy is basically what we sort of discussed just now. Okay, that means how do I manage a task to go from ready state to running to waiting or blocked and things like that. So there are different states that the OS needs to keep track of, okay, for every task that you introduce to the system. Then you also need to manage those challenges. All right, so that is where the core RTOS services comes in. So things like inter-process communication and synchronization. How do I ensure that data that is currently handled by task 1 can be safely accessed by task 2? Okay, again, this is very important, because if you do not handle data correctly, then what will happen is you can easily corrupt the data that you have. Okay, because in a real-time system, the task will switch in and out very fast, okay, many times. So you need to make sure that in the midst of all the switching that is going on, the data is still valid, it is still protected in the correct way. Okay, so these are things we will be looking at, and we'll also look at some other additional RTOS services like virtual memory and so on. Okay, so that is towards the later part of the module. Okay, in terms of the timing, okay, so basically what we are trying to show here is in a sense that for the ISR, okay, for the non-preemptive static, okay, each block here for ISR of course takes a finite amount of time, which we know, okay, and all the task level code, okay, basically is such that everything can be delayed, okay, by the same amount of time. Okay, that means since in a non-preemptive static, I go in a sequence, right? That means task 1, task 2, task 3, and so on. That means when task 1 is run, I will wait until the same amount of time before the next iteration of task 1. Okay, in non-preemptive dynamic, okay, the maximum delay that can happen is what? Depends on the maximum delay of any particular task. Okay, so for example, if task 5 is the task that takes the longest amount of time, okay, so that is the longest amount of delay that you may have to incur when you need to do a switching. Okay, that means if task 5 is running and then suddenly task 1, which is more important, needs to take over, I need to wait until task 5 completes before task 1 can run. Okay. In the preemptive mode, there is no form or very little delay at all. So there's really no overlap. Okay, because the moment any higher priority task comes in, you can immediately switch over. Okay, so there is very, very little time that you will be delayed. Okay, but so in terms of timing, of course, the preemptive dynamic is very good. Okay, but in terms of memory, if you look at this, for both this and this, okay, at any point of time, only one of the tasks will be running. Okay, because when any task runs, so for example, if task 2 is running over here, and suddenly I say that task 4 is more important, okay, task 2 will still finish and then task 4 will run. Okay, so the amount of memory I need is such that it depends on the maximum amount of memory that any of the tasks require. Okay, but for preemptive dynamic, you can continuously be switching, okay, across all the tasks. That means, for example, task 4 is running, but before I can finish, I get interrupted, okay, because I say task 3 is more important. Then task 3 is running. Then before I can finish, suddenly something else happened. Task 2 is more important. And before I can finish, suddenly something else happened, and task 1 is more important. Okay, so at any point of time, task 2 could be halfway done, task 3 could be halfway done, task 2 could be halfway done, and now I'm doing task 1. Okay, that means I need to have sufficient memory to hold the status, all right, or the context of each of the tasks, such that when I'm switched back to those tasks, I can continue from where I left off. Okay, so in terms of the stack space, you can see that I need enough stack space that is required by all of them together. Okay, I need to add up all of them. All right, because at any point of time, I can switch out of any of the tasks. Okay, so I need to be able to continue from where I left off when I go back to that task. Okay, so that is the memory requirement. Okay, if for the preemptive dynamic mode. Okay, so that brings us to the end of this chapter. Again, this chapter is just to give you some overview of what we are trying to achieve, all right, and why we are trying to go in this direction. Okay, and the scheduling policy we will actually be discussing in a lot more detail later on. All right, but it gives you the idea that, okay, to move towards what you are used to doing, okay, the static scheduling approach to something that is preemptive and dynamic is very challenging. All right, and that is where the OS comes in, because the OS helps us to manage all of this in the back end. All right, and we focus on the application we want to develop. All right, so that is basically the objective of this chapter. Okay, so just before we end and move on, I just want to highlight this. Again, this is because I think some of you may not be aware that about 2 semesters ago, the TA system has been updated. All right, so in the past, you can apply to be a TA just 1 week before the semester start, and you can still go through and you can still get selected. Okay, but now things have changed. All right, there is a lot of admin work involved. There is some academic screening that the students have to be cleared off and things like that. All right, so towards the second half of the semester, usually you will receive an email from the SOC side, okay, asking you to express interest to be a TA. Okay, you need to make sure you, so this is for all the modules, whether it's this module or any other module you want to be a TA, you need to apply early, because they need to capture your thing and need to do the background check. Okay, because only after that is done and you are approved, then the module coordinators will be able to see your name in the list. Okay, so if you miss that, it's very difficult already. Okay, then you cannot be a TA for that whole semester. Okay, so if you want to be a TA, let's say next semester, when you receive that email this semester, you need to apply, and you need to do this every semester. Okay, it is not guaranteed renewal. Okay, that means if you apply this semester and you get approved, so next semester you can teach, correct? But again, if you want to teach again, you need to apply one more time again. Okay, so every semester they need to do this sort of screening, okay, of new TA applications. Okay, so that is just for you. Okay, so this is for all the modules. Okay, not only for this. So there's a question, is a way of teaching, the change in the way of teaching since last semester. Okay, so this current set of materials is basically already there for at least the last 4 semesters already. Okay, so the last few recent papers or past year papers all are valid. Okay, so for the last at least I think 4 semesters, this is the content already. Okay, if you go beyond that, okay, then probably you will see that that was the earlier version where they use Arduino Uno and they use the free RTOS. Okay, so I used to teach that for I think 2 semesters, and then after that we switched to this already. Okay, so I think if you look at the last 2 years worth of papers, that sort of gives you a good idea of the type of questions and things like that. Okay, so is there tutorial this week? There is no tutorial this week. Our tutorials will start next week. Okay, but this week we have the lab. Okay, which I will talk about in a while. Okay. Okay, so the papers and all I will release at a later time. All right, the past year papers. Okay, so that when you look at it, you are able to relate to it a bit better. Okay, so I won't release it now, but I will definitely release it. Okay, over time. Okay, so before we move on, before I go for a break, I just want to do this one thing first. This one activity. Okay, so the next chapter is this on the Cortex M0 Plus CPU Call. But before we start, I have this one activity here that I want to discuss with you. And this is important, all right, just to understand why in the context of the lab. All right, so in this picture, you observe that something that you do every day, all right? You put your phone to charge. Okay, so this is what you do every day, probably once in the morning, once in the evening, or so on. Now, if you do this, okay, so let's say later on you try to plug in your charger to the phone and you see that it is not charging. If you see it's not charging, okay, what do you do? Okay, can you share with me what will you do? Okay, so as silly as it may seem, just share with me what will you do if you try to plug in your charger and you don't see the phone charging? Buy new phone. Okay, nice. Okay. Okay, so don't ask me, don't ask me. But okay, I think most of you get the idea correct. Check wall plug, check cable, plug out, plug in, try again. Calling for mom might work. I don't know. Okay. Blow into the phone hole and plug again. Yes, might be. Okay, because maybe there's some dirt or something that is stuck there that is preventing the connection. All right, change cable and so unplug and replug. Okay, so good. All right. And why did I want to bring this up? Okay, why did I want to bring this up? Okay, because this mindset is something that is very important when you are working on a project. Okay, because one thing I've observed over time, all right, is that especially in the project, you run the code, all right, okay, and I will generally give the code to make sure some part of it works. And what you will do is you will run the code, and then when you see that it doesn't work, you will tell me, oh, the code doesn't work. Okay, and then you will just stare blankly and say that, oh, it just doesn't work, and then you don't know what to do. All right, so if it doesn't work, okay, if things don't work the very first time you put things together, you run the code, then you need to troubleshoot. You need to figure out what is the issue. All right, so that is where the technique of figuring out step by step what happened. Okay, so of course in embedded systems you have hardware and you have software. So firstly you check the hardware, whether your connections are correct, the wires are correct, the power supply is switched on, all these things you check. All right, and then if the hardware you have confirmed correct, then you look at the software. All right, and then you try to see whether did you configure the registers correctly, did you miss out any of the settings? All right, and then if things all seems correct, then you go ahead and try to do some other troubleshooting. You check, use a multimeter, check the voltage, use the oscilloscope, check the signals and things like that. Okay, so you need to develop this sort of good mindset to say that we have to troubleshoot to figure out what went wrong. Okay, of course I will be there, the TAs will be there, all right, but of course we can't sit down and troubleshoot everything with you, all right? So we can check, we can ask you to check certain things, all right, and then from there we try to narrow down to see what is the issue. All right, so again, why this is important is because if things don't work, it is fine, all right, but definitely you can figure out what is the issue and then you can get it to work, all right, but you need to put in some effort in that direction. Okay, so let's go for a break now. All right, we'll go for a break and then we will come back and then we will discuss this chapter. All right, and I will also talk on the new specification as well as this week's lab activities. Okay, so now it's going to be 10:50. Okay, so I think we can go for a 10 minutes break. Okay, at 11 o'clock we'll come back and then we will start with that chapter, and we also look at this week's lab activities. Okay, so I'll see you all back here in 10 minutes time. All right, so if you have any questions, you can still put in the chat. Okay, after the break, I will address those questions. Okay, so welcome back after the break, and let's continue, all right, with the chapter 3. Okay, to have an overview of the CPU. All right, so usually all my lectures, what I will how I manage it is towards the last part is I will do some demo related to the lab that you will be doing for that particular week. All right, so because of that demo, what happens is usually it stretches all the way to maybe 11:50 or 11:55. All right, so those of you who need to log off because you have another class and things like that, you are free to log off, okay, earlier. If you want to look at that demo part, you can always look at the recording later on. All right, but if you don't have anything after this, it's always good to stay till the end. Okay, but if you have to log off, please go ahead. All right, so the lecture part usually is done by about 11:35, 11:40, and then I will do some demo after that. Okay, so let me go ahead to review this. Okay, so this is basically just a quick and short overview of the processor core that we're going to be dealing with. All right, for this board. Okay, again, we switched to this processor because again, it is important to have a good sort of background in different processor cores or microcontrollers. So Arduino is something you're already familiar with, right? So switching to a Cortex or ARM-based controller adds a lot of value, right, to your own profile and your resume. So this is something that is I would say a good value add to you as an engineer. All right. So in this lecture, we are just going to go through some very basic stuff, all right, of the processor. I think in other modules, you will be learning more in depth into the ARM internal registers and how to do assembly language programming and things like that. All right, so that is not covered here, but you will be doing that in some other module. Okay, so the idea of a microcontroller and microprocessor, I think we have done before. I mean, we have seen before. So this is the processor core. Okay, by itself, okay, it is just a workhorse. All right, that means it is in charge of executing all the instructions and giving you the output and things like that. All right, but it cannot function alone. All right, at the very basic level, you still need some memory, all right, to store your information. So this is at least a very basic requirement. Of course, the interconnections are not something we're looking at, but if you done computer architecture modules or you'll be doing it, all right, the fundamental internal connections between the core and everything else is basically 3 different buses. Does anybody know what are the 3 buses? Okay, 3 buses that connect the core with everything else. Okay, does anybody know what they are? yeah, address, data, and control. Okay, so these are the three main buses. Okay, again, this is more for you will study more in detail when you do computer architecture modules. All right, but these three buses generally connect the core with everything else that you see here. Okay, so at the very least, you need the core with the memories. All right, and when you have all these other add-on peripherals, you have a more complete system. All right, to do a lot of things within that single chip itself. Okay, so rightfully, if you build your own board, okay, you can actually make it very, very compact. Even if you look at the Arduino Uno, the board is actually very big. Okay, the board is actually very big. All right, if you look at the Arduino Uno, for example, okay, since we are familiar with that, but the chip itself is only that small single chip. So if I want to build my own custom board, all I need is to extract out that chip. Okay, put the power and the ground. Okay, and that's about it. Okay, if I want, I can put in an external crystal or external clock. Okay, so if you remember, your board runs at if I'm not wrong, 16 megahertz, the Arduino Uno. But even if you don't want that, you can configure it to use internal clock. All right, so just that chip alone with a power is actually enough to build your own custom board. All right, the Uno board itself is very big because they just have a lot of other stuff there. Okay, but all that is not necessary if you just want to build it as a standalone system by itself. All right, so the M0 plus core itself, again, these are the internals, but we are not going into all of that. We are just going to learn a bit about this internal core. And in the next chapter, we're going to talk a bit about the interrupts and how it works with the NVIC. Okay, the rest of the stuff we're not going to go through. Okay, in terms of the architecture, okay, is what we call a load store architecture. All right. And in terms of the processor itself, we call this a RISC processor. So you all should know what is RISC, correct? Can anybody tell me what is RISC? Yeah, reduced instruction set computer. Okay, so there are two types. One is RISC and CISC. Okay, so in the past, CISC used to be more popular because you can write complex instructions to be executed. Okay, but with ARM, okay, with ARM coming along, all right, they sort of revolutionized the RISC to show that it is actually very efficient to use RISC because you can get things done, okay, at the same efficiency with very, very low power consumption. Okay, so that power consumption factor is actually one of the main reasons why RISC and ARM have sort of dominated the processor landscape across the board. Okay, so even though ARM was very popular for handheld devices, okay, with the introduction of the Apple's M1 chips, all right, we see ARM also invading the PC space. All right, so I think it's quite an interesting transition. All right, and also it's interesting because definitely the big players like Intel and AMD will also want to compete and show how power efficient and how effective their processor cores can be, okay, against ARM. Okay, so I think it's an exciting time, all right, that we will get to experience a lot more advanced and capable architectures in the future. All right, so in RISC, since it is a reduced instruction set, basically it follows this concept of what we call a load store architecture. That means whatever information you have is inside your memory. Okay, and what you need to do, let's say if I declare variables X and Y, all right, I need to take this data and put into my internal registers, R1, okay, R2, and so on, into my internal registers, process the data, and once I get the data, so let's say if I do an add operation, and then the result I can put back into the other register here, Z. Okay, so it is basically what we call a load store architecture. All right, and again, to support that, you have quite a lot of internal registers. All right, so you, as much as possible, keep the data within the internal registers as much as you can. So again, this is the internal processor core registers. Again, you have the 12 general purpose registers together with the others here, the stack pointer, link register, PC, and so on. Okay, so all these are not going to be tested. Okay, you don't need to know all these register details and things like that. Okay, we are not covering all of that in this module. All right, but this is just to give you an idea of what is happening at the lower level of the core. All right, so these are all the registers. Okay, so again, we are not bothered about all this right now. Okay, when you are doing other modules on computer architecture and assembly language programming, you will go more in depth into how to use these registers to do assembly language programming. Okay, so assembly language programming is of course a very painful language to learn. Okay, but it is also very, very good because you really get to see how things are being done at the lowest level. All right, so it's really interesting, a very nice course to take. All right, when you go about doing it. Okay, in terms of operating mode, okay, there are two types of mode. So the default mode is what we call the thread mode. All right, you come out of it in reset. Okay, the moment you have an exception, so exception is also another way to term interrupts. Okay, so exception or interrupts, you switch to what we call a handler mode. All right, so again, all of this is sort of handled in the back end by the processor. Okay, whenever you are switching and handling interrupts. Okay, in terms of the registers, we have some core registers. Okay, again, these registers are to hold some important information whenever you are performing some activity. All right, so for example, when you are performing any arithmetic or operations, you will update these flags, okay, to say whether it is a 0 or a negative or things like that. When you're handling exceptions, the exception number will be handled here. And to switch between thumb and arm mode, okay, you have another register here. Okay, again, these are updated automatically, okay, when you are handling interrupts or when you have an outcome of a operation and things like that. All right, these are to prime mask register here is to configure masking of interrupts. Okay, so if I want to disable interrupts, okay, I can update the prime mask register to either disable or enable interrupts, okay, depending on what I'm trying to do. Okay, and there are specific instructions, okay, in the C or assembly level that allow you to access some of these registers. All right, again, we are not going to touch all of this. All right, we're going to just leave it as it is. In terms of control, there is a mode called privileged mode and unprivileged mode. Okay, again, this is something that is interesting. Privileged and unprivileged, what does it mean? All right, when you say you are operating in privileged mode, okay, that means the processor is in privileged mode. Okay, that means you have full access to do anything. All right, that means you can go in and control every single register, every single setting. When you are operating your device in unprivileged mode, okay, or you have only unprivileged access, then you can use the processor, okay, but you are not allowed to perform certain actions. Okay, so again, this is very applicable in, let's say, in your smartphone, all right, where you have your OS that's going to run in privileged mode, but the apps that run on it have to be unprivileged, all right, because you do not want an app to go in and mess with your system settings that can corrupt your phone or hang your phone or things like that. All right, so there is some mode of operation depending on how you configure the processor. Okay, the next thing is the memory map. All right, so this is in the past I used to have one part of the lecture dedicated to talk about how to design memory map decoding circuitry. Okay, but I took that out, okay, because it's not enough time to cover that anymore. All right, but in memory map, basically what it tells us that, okay, in my device I have this much of space. Okay, now if I take the microcontroller, the processor core by itself, okay, if I just take the Cortex M0 plus core by itself, and I say I want to design my own embedded microcontroller. All right, then I can decide and I can choose how I want to make use of this space. Okay, I can decide and say, okay, from one address to another address, I'm going to place my IO devices, I'm going to place my RAM or things like that. Okay, so I have the flexibility to decide. Okay, but when we are dealing with prefabricated microcontroller like this, which is the KL25Z. Okay, so the KL25Z is the name of the microcontroller. Okay, and that microcontroller is running on the Cortex M0 plus core. So the microcontroller, when it was designed, okay, the designers already preset the memory map for us. Okay, so they already decided that okay, memory will be from here to here. Okay, peripherals are from here to here, and so on. Okay, and these addresses are actually significant. Okay, because they relate to where the registers are located. Okay, and that ties into the coding which we'll be doing later. All right, so when we are starting the peripheral subsystems and all with the GPIO, we were going to go in depth into understanding a bit more of these addresses and how to extract this information from the data sheet as well as the KL IDE that we'll be using. Okay, so we will explore this memory map in more detail over time. Okay, so another important thing, okay, that always confuses engineers, okay, which you should know is the Indianness. Okay, so what is Indianness? Okay, so there's two variations to this. One is called the Little Indian, the other is called Big Indian. All right, and this basically specifies how I store multi-byte value. Okay, so when I have multiple bytes, all right, so if I take a 4-byte value. Okay, so if let's say this is address 0, 1, 2, and 3, and inside this I store this data called AA, BB, CC, and DD. Okay, this is a 4-byte value. Okay, that means if I declare this as a maybe a 4-byte integer X. Alright, so this is the actual value that I have. Okay, so X, if I look at it in the hexadecimal form, it will be like this: AA, BB, CC, DD. Now, in my code, of course, I write it this way and I can access it this way. But how does this 4-byte value get stored in memory? Alright, how does it get stored in memory? So that depends on how the Indianness of the system that you are dealing with, okay, or the processor core we are dealing with. Okay, so for a Little Indian system, okay, the least significant byte is stored in the lower address. Okay, so if let's say I want to take the address, okay, so let me write the address in here. Okay, so let's say this is address A000, A001, A002, and A003. So these are 4 memory addresses. Now, if I were to say that I want to use it as Little Indian format, okay, in Little Indian format, the least significant byte will be stored in the lower address. So DD will come here, CC, and BB, and AA. In the Big Indian, it will be other way. Okay, the least significant byte is in the highest address. So DD, CC, BB, and AA. Okay, so of course, at the highest level, okay, when you're just dealing with C programming, it doesn't, if you're just dealing with it as a 4-byte value as a whole, of course, it doesn't really matter. Okay, but if you want to do byte level access, okay, you want to look at individual memory locations to extract out certain information, then understanding how the data is stored can actually make a difference, okay, between understanding what you are accessing and what you are, or which actual byte you are trying to access. All right, so this is again important, okay, to just understand how multi-byte value is actually stored in a at the memory level. Okay, so this again a common confusion among many engineers. So just remember this. Okay, least significant byte is stored in the lower address for Little Endian. Okay, when we're accessing it as a 4-byte value, it doesn't matter because you will automatically take it as the value that it is. Okay, so for example, if I take another variable y and assign it to x, this 4-byte value goes into y. Okay, so whatever value is x will go into y as it is. All right, but if I want to extract out certain bytes, okay, then it matters as to whether I store it as Little Endian or Big Endian, because then you need to know which is the byte order that we are referring to. Okay, maybe I'll write up some code to demonstrate to you how it works next lesson. Okay, so you have a better idea how to appreciate this. Okay, so let me work on something. I'll demonstrate to you. Okay, so for in this case, our processor that we're dealing with is Little Endian. All right, again, we don't really need to worry about it. All right, because everything is handled in the back end. All right, unless you are doing specific byte level access. Okay, so this is just to give you some background about the thumb and thumb2 instructions. Okay, so basically, if you look at it, when ARM came out, okay, when ARM was launched many years ago, it was a 32-bit architecture. Okay, again, when you deal with 32-bit architecture, what does it mean? It means that your processor core is 32-bit. Okay, when your processor core is 32-bit, it also makes sense to deal with 32-bit memory. Of course, you can deal with 16-bit memory or 8-bit memory, but it's more troublesome. Okay, so if you have a 32-bit architecture, dealing with 32-bit memory is a more straightforward approach. Okay, but many years ago, memory was quite expensive. All right, so 16-bit memory was a more affordable option for many engineers. All right, so to support 16-bit architectures, okay, ARM introduced the thumb instruction set. Okay, of course, then along the way, memory again became cheaper and more affordable. Okay, but then now you have a mix, correct? You have some group of people with ARM working on ARM instruction set, some group of people working on thumb instruction set. So that is where in 2003 they came out with this thing called the thumb2 instruction set. Okay, it basically sort of combines both together. So you can run your thumb instructions or ARM instructions on this new instruction set, and both will work fine. Okay, so again, this is just the history of what happened and why you have these 3 variations. Okay, ARM, thumb, and thumb2. Okay, again, this only matters mostly if you are dealing with low-level assembly language coding. Okay, since we are writing in C, we don't really have to worry about this so much. Okay, again, this is some information about the Cortex M0 Plus. All right, so in Cortex M0 Plus, it by default, okay, switches in thumb mode. Okay, again, this is at the lower level, so we don't need to worry about it. All right, but we just need to again, I just put it here for information only. All right, that you can just take it as info. You don't need to worry about it so much. Okay, again, this chapter I didn't go into too much detail, like I said, because to go into the details of the architecture is one module by itself. All right, so that is something that you will probably study somewhere else. Okay, so just 2 things. The KL25Z board, okay, I'm going to show you and discuss about it now. All right, but if you can, it'll be good to do a 3D printing for your board to protect it. Okay, again, why? Because when you start testing the robot on the RAM, many times your robot will commit suicide by falling off the RAM. Okay, and if your board is not protected, you run the risk of damaging it. Okay, and then it becomes a huge stressful moment for you. Okay, so if you can 3D print some casing, okay, I think the Makers Lab, I think all of you should have access. Okay, and you can print it, and I think you can protect your board. It'll be good. Okay, so of course, when you do the 3D print, you also need to factor in the space you need for the connectors, the wiring, and things like that. All right, so this is just something for you to consider. Now, let me go through the product specifications update, and then I will talk about the lab one. Okay, or what you need to do for this week. Okay, so just give me a minute here. Okay, so this is the updated product specification that I've uploaded just now. So it's updated today, 19th January. Okay, so the only update and the main update is this. Okay, this section here, which is the obstacle that you need to prepare. Okay, and this is basically for the challenge run 2. So if you remember challenge run 2, you're supposed to in self-driving mode go straight towards the obstacle, go around and come back. Okay, and it has to pass the start and stop line to be considered as a valid run. Okay, so this obstacle over here, in the past, I used to put those small soccer cones, okay, as the obstacle. But I think we have a lot of highly enthusiastic soccer players in our students, so the cones kept disappearing. Okay, so and to make it easier for everybody, I decided that you will create your own obstacle. Okay, and you'll be standardized with using 4 toilet rolls or kitchen rolls taped together in a square shape. Okay, so I think this is quite standard, so we can't really go wrong. So you just take 4 either toilet rolls or kitchen rolls, all right, and you tape them up together, okay, to create this square block. And you have the flexibility to cover up the obstacle with any type of color or any type or any color of paper. All right, so again, this is to your benefit because whatever sensor that you're going to be using, okay, to detect the obstacle, you can sort of calibrate it based on your own chosen surface that you are going to use. All right, so there is no issue of it works on yours but it doesn't work on mine and things like that. Okay, so you decide and you bring along your own obstacle. Okay, so this is basically, I think it works in your favor to keep it this way. All right, so this is just something for you to prepare. You don't need to do it now. All right, probably when everything comes together, which is after the midterm break, then you want to look at this. All right, now the next thing is the lab one. Okay, so before we go to the lab one, okay, which is this Friday, okay, let me show you the board, okay, that you're going to be using in our module. Okay, so this is basically the freedom board, okay, that you're going to be getting. Okay, when you get the board, okay, okay, so let me show you here. You are not going to have these connectors. Okay, these connectors are something that you need to solder on. Okay, so you'll be issued the connector. So it's just a bare board. I mean, not a bare board, but without the connectors. All right. Now, the soldering, again, you will see that you have solder pads on both sides. Okay, so you can solder this way or the other way. Okay, if I'm not wrong. Now, ideally, you should solder it this way so that it's easier for you to tap on the connectors, and this is the back end of it, correct? So keep this side as the soldering side. Okay, of course, no matter what I say, some of you will still go and do it the other way around. All right, so please be careful. The other thing is your soldering itself. Okay, some of you, if you are not confident of your soldering, okay, if you are a bit concerned about it, then I would strongly suggest you get help from one of your teammates or somebody else in the lab to help you with the soldering. Okay, so as much as I want you all to be good in soldering, you can practice on your own using other spare prototyping boards and things like that. Okay, but do not practice it on this board. Okay, because if you do not solder it properly, okay, and you create let's say short circuit along the pins over here, okay, you need to desolder and then you need to resolder again, and then there's a high chance you might damage the board. Okay, So for the board itself, the soldering of the connectors, I would strongly encourage you to either do it if you're confident, okay? If not, get help from somebody else just to do this part alone. All right. Again, the main concern is I do not want you to damage the board even before the lab start. All right. You do not need to rush and do soldering this week. Okay. The first, next week's lab, which is on the RGB LED and so on, does not require the soldering. Okay. So you do not need to worry about that. Okay, so is lab 1 graded? Okay, none of the labs are graded except for the one which is the demo requirement. Okay, so none of the labs are graded. The only one which is graded is the one which is the demo requirement, where you need to show a few things put together. All right. Now, in the past, okay, to communicate with this board, we had a Bluetooth module integrated. You had to connect a Bluetooth module to this to use the app to control your robot. Okay, but the Bluetooth module was always giving some issues. All right. So as of last year, just to make things a bit more exciting, I introduced another board. Okay, which is the ESP32 board. All right. So it gets more exciting. I wanted to make it even more exciting by running 2 different OS at the same time. Okay, so one OS on the KL25Z, one OS on the ESP32, but I haven't had time to work out the details yet. All right, so you don't have to do that. Probably next batch will do that. Okay, but for now, the ESP32 is there to provide you with the ability to have a Wi-Fi connection with your KL25Z. All right, so this ESP32 board is there specifically as a Wi-Fi bridge to say. Okay, how it works, how to configure it, everything. I already prepared all the lab manuals, which I will release at a later time. All right, so we are not going to touch the ESP32 for now. Okay, we're only going to touch the KL25Z. The ESP32 will be issued to you later. Okay, when we are putting things together, okay, and making everything work. All right. But for now, you will have 2 boards, KL25Z and the ESP32, to work on your project. All right, so for the KL25Z, okay, let's look at the lab 1 now, okay, to understand what is going to happen. Now, when you get your board, okay, so this is the lab manual, so you can go through. So the first thing is you need to, okay, so another important thing I might also mention is that you need to be very careful with not touching the back of this board, okay, or touching the components with your bare hands. All right, so this board is quite sensitive. All right, so be very careful. Do not place it on wet surfaces and do not touch it if your wet hands are moist or wet or anything. Okay, and do not hold it on the chips or anything. Just hold it at the sides like that. All right, so be careful with this board. Okay, when you first get this board on Friday, okay, when you first unbox it, okay, you want to do unboxing video, go ahead, okay. But when you first unbox it, okay, it will come with a pre-installed software. Okay, this pre-installed software, what happens is when you plug it in, when you plug in your Freedom board into your laptop, it will actually show up like a normal flash drive. Okay, it will show up like a normal flash drive. So that is the default setting. Okay, and why does it show up like that? Because by default, it is designed to work with the Embed OS. Okay, if you remember last week, I showed you the Embed OS. So the Embed OS is basically another OS that again abstracts everything and makes life very easy. All right, and in that mode of operation, your board behaves like a flash drive. So when you build your code, you just drag your code to the flash drive and you reboot with a new code. Okay, but that is not going to be our mode of operation. We are going to use the we're going to use the Kale IDE to program the board. Okay, so you need to download the KL25Z. Okay, I would strongly suggest going directly to the Luminous directory. Okay, don't go to the website link because it might have a updated version which may have issues. Okay, so go to the Luminous directory, okay, on the software installation and download that to install on your system. Okay, so once you install it, okay, you need to do some configuration here, which I've explained. And what we are doing here is basically to make sure that your KL25Z, instead of uh, showing up as a flash drive, will show up as a proper hardware board, okay, with the onboard debug enabled. Okay, so we need to do this step, all these steps outlined in this document very carefully, step by step. All right, because we need to make sure that the board is now configured to be used with the Kill IDE application. Okay, if you don't do this step properly, what happens? I mean, all these steps correctly, your board will still show up as a flash drive. Okay, if it shows up as a flash drive, you can't use the Kill IDE. Okay, and you can't work on the labs. So you need to make sure you do this step correctly. Okay, and make sure the software is installed correctly on the system. So everything is sort of explained very cleanly and very nicely here. So just follow all these steps. All right, and once you see all these steps, okay, by default, okay, when you first unbox it and it shows up as a flash drive, you will see that the board actually has the RGB LED, which will react to the accelerometer sensor. Okay, so when you are shifting your board, by default, the RGB LED over here, okay, will actually change colors. Okay, so that is the default code. All right, so that sort of confirms that the board is working. All right, and once you update with this new mode of operation, okay, you will be able, and you run the code that is given to you, you should be able to see the RGB LED is blinking in a particular sequence. Okay, so all this is important for you to test and verify that the board is working. Okay, so you don't need to rush and do any soldering this week or next week also. Okay, but the week after next is where you need to do you need to have some of the soldering done, because you're going to use the pins. Okay, so for this week and next week, you can still be without the connectors. Okay, so this Friday, okay, when you go to the lab, okay, this Friday when you go to the lab, a few things. So the first thing is, when you draw out the board, you can draw out for your teammates if you want. Okay, if you want to draw for your teammates, it's possible, but whoever is going to draw out, is your responsibility to check that the boards are working. Okay, so once you draw out for your teammates and you leave the lab, it's considered that all the boards that you took with you are working. Okay, you cannot come back later and say that, oh, I did not test, I go home and test, then I realize it's not working. Okay, we can't do a swap for you at that time. Okay, so each person will have one board. Okay, it's one board per person. Okay, so within your team, you have 4 team members. Okay, so if you collect as a team, you can collect 4 boards, or if you want to connect individually, it's also fine. All right, but just note that whoever is going to collect, it's your responsibility to check the boards that they are working before you leave the lab. Okay, so once you leave the lab, it's considered the boards are working already, so you cannot come and ask for a swap later. Okay, so again, this is important if you're asking your friend to collect on your behalf. Okay, so that is what is happening this Friday. So you do not need to stay for the whole 2 hours. Okay, you come, you collect the board, you test. Once you are happy, you can leave. Okay, you do not need to stay for the full 2 hours. You just want to make sure that each of you have your own board and it's working. All right, so that is quite easy for this Friday. Okay, then then the soldering part, like I said, you can, if you want, you can do it. Okay, if you're confident. If you're not, you can work on it the next week. All right, let me see anything else. Yeah, so I think that's about it that we have. For the software, again, install it from the version that we have in the Luminous. Do not download any updated version from the internet. Okay, in case there are compatibility issues. All right, again, also, like I said, please be careful with the board. It's very sensitive. Okay, we do not want you to damage the board, okay, before we start doing much with it. Okay, so everyone will collect their own board. Okay, and you have to test the board before you leave the lab. I will be there this Friday as well. Okay, so if any questions, you can also ask me. Okay, so that's all we have for today. If anything you want to ask, you can ask me, or I can put in the chat. Okay, if not, thank you. I will see you all on Friday in the lab. Okay, so this Friday, you don't need to stick with the work from home schedule, okay, because you're not going to be staying there for the whole time. Okay, so all your team members can also come if they want to. Okay, so the software is currently only works on Windows. Those of you who have Mac, okay, I believe all NES students have access to one of the virtualization software. I can't remember, it's virtual box or something like that. Okay, so students have a license for that, which you can install and run the ID on that. Okay, so for those who don't have Teams, not to worry. Okay, if after this Friday you still don't have a team, I will assign randomly to those who don't have. Okay, so I will do a poll to get all your names, and then I will assign you all to teams. Okay, so I'll group you all together first, and then after that I will assign you all to teams that don't have a full four-member team. Okay, the work from home schedule, yeah, you need to choose one person to stay home every week. Okay, but for this week, it's not necessary because you're not going to be there for the full 2 hours, so it is fine. Yeah, all our lectures are recorded, will be uploaded to YouTube, and I also send you all the Zoom link as well, so you can choose either one to watch. Okay. Okay, for lab demo and final assessment, I will finalize that at a later time. Okay, the work from home. Okay, for final assessment, definitely you don't need. Okay, everybody can come. Okay, for the lab demo part, I will confirm again at a later time. Okay, so looks like no other questions. So thank you. I'll see you all next week. Also, I'll see you on Friday for the lab.